This video is to help you through the activity on reaction energy diagrams and chemical reactions. Before we start looking at reaction energy diagrams, let me remind you about how chemists represent changes. This left to right format of the reaction progress is how we list it on a reaction energy diagram as well. A reaction energy diagram is simply another way to show a reaction. There is a set of X and Y axes where reaction progress is listed on the X axis, and just like in a chemical reaction, you show the reactants on the left and the products on the right. So the X axis here is reaction progress from reactants to products. On the Y axis, we show energy, increasing from bottom to top. We will represent reactants and products on this diagram, and the level on the y-axis will represent how much energy they have. Low means low energy or more stability, and high on this chart means high energy or very highly reactive, not very stable, in other words. Here I've shown reactants and products with a line representing their relative energies. In this case, I've shown the reactants at a slightly higher level than the products. Sometimes we'll just label these as reactants and products, or sometimes you can even see the actual chemical structures listed on the diagram. The reason that we can list these things with relative energies is because molecules have energy associated with them. We won't be talking about quantitative amounts in this class. So in other words, we're not going to be giving you the actual energies of the reactants or products. We will just talk about them in relationship to one another. Once again, this diagram shows that the reactants are at a slightly higher energy level than the products. Now, in going from reactants to products, we don't simply just connect the lines because there's not just a direct energy path from the reactants to the products. In fact, any change from reactants to products involves some energy input. And this energy input is represented by a little increase in energy or a little hill on our reaction energy diagram. So anytime you're connecting the reactants to the products, you draw a little hump in between the two. Now, the top of this hump represents something that we're going to call a transition state. It's the transition between the reactants and the products. The height of the hill tells you how hard it is to go from reactants to products. And so one of the things we're going to focus on in this activity is the difference between the top of the hill and the starting place, or the reactants. This difference is called the activation energy, or it represents the energy that it takes to overcome some barrier in order for reactants to turn into products. The other important difference in this chart is the difference between the reactants and the products. This tells you how much energy has either been given off or consumed overall. It's the total energy change of the reaction, and it's also called the Gibbs free energy. It's also represented by a delta G. These are the main components of a reaction energy diagram, and these are the things that you will want to know about. Let's talk about the activation energy. When molecules react, they have to collide with one another. And for a reaction to happen, they have to collide in the correct orientation and with enough energy to break bonds and reform new bonds. There's a diagram in your textbook that tries to explain this. And here it is. This is the activation energy, or this is a cartoon that's explaining activation energy and what it means. If you get familiar with this and understand it, it can help you later on this semester when we talk about enzymes and how they catalyze reactions. This cartoon is trying to show you that reactant A needs to collide with reactant B in order for a chemical reaction to form. But they have to collide in the correct orientation. In this cartoon, this and this are the reactive sites of A and B. If they don't collide in the correct orientation, they will simply just revert back to the starting material or the reactants. So no reaction will happen. So they must collide in the correct orientation. Now, if they collided with the correct orientation where the reactive parts are lined up, if they're not colliding with enough energy for bonds to break, they will simply go back to reactants and no reaction will happen. So for a reaction to happen, reactants must collide with the correct orientation, but they also have to collide with enough energy in order to break and form new bonds so that they can form product. When we're talking about energy, one way to talk about it is in molecular motion. Molecules are always moving, and the faster they move, the more energy they have. And the more energy they have, or the faster they move, the more likely they are to run into each other more often and in the correct orientation. And the faster they move, the harder they hit each other. So when molecules are moving very fast and they have a lot of energy, they're much more likely to run into each other in the correct orientation and with enough energy to form product. We know this as temperature. The faster molecules move, the hotter they are. So when we think of something being very cold, know that molecular motion is slowed down compared to when things are very hot or we add heat to them. What we're really doing is making the molecules or atoms move more quickly. So heat is one way that you can increase the collisions and increase the force with which molecules collide in order to form product. This is one reason that we heat things to make reactions happen faster. Remember that energy is required for collisions to happen in the correct orientation and with enough energy to break bonds. This is what we call activation energy. Here's the diagram again, showing activation energy and the Gibbs free energy, or the total energy change. These mean two different things, and they are very independent of one another. The activation energy is related to something that chemists call kinetics. It tells you how fast a reaction will happen. And I could change the height of this hill without affecting the value of the reactants or the products. On the other hand, thermodynamics is represented by Gibbs free energy. And this tells you basically the relative energy levels of the reactants and the products. This is telling us how spontaneous a reaction is and whether it releases energy or absorbs energy overall. Let's talk a little bit about this delta G value. The delta G is defined by the energy of the products minus the energy of the reactants. Let's just talk about this in a qualitative sense. If the energy of the products is larger than the value of the reactants, then you're subtracting a smaller number from a larger number, and this will give you a positive value overall. This positive value has meaning, and I'll show you that on my next slide. On the other hand, when the energy of the products is less than the energy of the reactants, you're going to be subtracting a larger number from a smaller number, and that will give you a negative value for delta G. The positive and negative values of delta G tell you something about spontaneity. Here are two reaction energy diagrams that you have on your activity in front of you. I'd like you to focus on the second diagram for a moment. And I'd like you to notice that the reactants here are lower than the products. This means that the reactants have a lower energy than the products, and the product value is higher or larger than the reactants value. In this case, we're falling into the first category, where the energy of the products is more or greater than the energy of the reactants. This is going to give us a positive delta G. A positive delta G is a reaction that's going to be referred to as endergonic. Whenever you notice that reactants are lower in energy than products, this is going to be an endergonic reaction. You may have also learned this as an endothermic reaction. Endergonic and endothermic are nearly synonymous. They mean almost the same thing. Endergonic is simply a more general term. In this first reaction energy diagram, I'd like you to notice that the reactants have a higher energy or a greater value for energy than the products do. In this case, we're falling into the second category, where delta G is negative. This is called an exergonic reaction. Exergonic means that there's a negative delta G, or that the reactants are a higher energy than the products. This is also synonymous with exothermic. You may have learned before that a reaction that looks like this can be exothermic. Exergonic and exothermic are nearly synonymous, but exergonic is a more general term. The value of delta G tells you something about the spontaneity of a reaction. Exergonic reactions are spontaneous reactions. Any system wants to acquire the lowest energy possible. When reactants go to products here, they lose energy and energy is given off. And these more stable products are kind of like happier than the higher energy reactants. These are reactions that overall give off energy, and they are spontaneous, or they'll happen spontaneously. On the other hand, endergonic reactions are not spontaneous. Overall, they consume energy to bring reactants all the way over the activation energy to a higher energy level as the products. So overall, they consume energy and they are not spontaneous. These are terms that you want to get to know. It's a good idea if you associate the negative delta G with the word exergonic and the word spontaneous, and the positive delta G with the word endergonic and not spontaneous. These terms are referring to the thermodynamics of the reaction, independent from the activation energy or the kinetics of the reaction that tell you how fast it is. Now let's talk about the kinetics. Please pause the video and read number 3 on your activity. In number 3, I'm asking you to draw a reaction energy diagram of a catalyzed and an uncatalyzed reaction. There's a blank box for you in order for you to fill out the reaction energy diagram. On my slide, I've written a reaction energy diagram for an exergonic reaction. I simply connected the reactants and the products using a little hump, and I'm going to call this my uncatalyzed reaction. There's an activation energy associated with this reaction that's shown by a difference in the reactants and the transition state energy, or the top of this hump. Now, what a catalyst does is it lowers the energy of activation by dropping the energy of this transition state. So if I would want to draw the catalyzed reaction, it might look something like this. It does not change the energy of the reactants or the products. It only drops the energy of this transition state, or the top of the hump, so that the activation energy is lowered. This makes the reaction faster because it's easier to get over the smaller hill than it is to get over the bigger hill. And so this green reaction profile would happen faster than the pink reaction profile. A catalyst does not affect the relative energy levels of the reactants and products, and so it does not affect Gibbs free energy. In other words, the total energy difference is unchanged by a catalyst. Only the speed by which the reaction progresses is changed. The activation energy and the Gibbs free energy are independent parameters, and number 6 in your activity is designed to show you how these things can be independent. Number 6 asks you to draw 4 different reaction profiles. I'd like you to notice that the first 2 ask for exergonic reactions, a slow exergonic and a fast exergonic. In order to emphasize the difference between a slow and fast exergonic reaction, I'm going to place the reactants and products at the same point on each of these diagrams. The important part for an exergonic reaction is that the products are at a lower energy level than the reactants. But in both of these diagrams, I'm going to put the products at the same level and the reactants at the same level. Now, the only difference will be that one is slow and one is fast. The larger the activation energy barrier, the slower a reaction will become. So the slow reaction has to have a bigger hill to climb than the fast reaction. This is what I would put. A very large hill to climb would have a very large activation energy barrier, and it would be slow. A very small hill to climb would be a very small activation energy barrier and very fast reaction. Both of these are exergonic, one is slow and one is fast. Pause the video now and try to apply this to the next 2 reaction energy diagrams. For an endergonic reaction, we need to place the reactants at a lower energy than the products. I'm going to place my reactants at the same energy level on both diagrams and the products at the same energy level on both diagrams to illustrate the difference between slow and fast endergonic reactions. Once again, for the slow reaction, I simply need to put a bigger or higher hill than the fast. Here is an endergonic reaction that has a very high hill to climb to reach the products. Therefore, it will be slower than this reaction where the hill is not quite as high. Notice that an endergonic reaction can be either slow or fast, and an exergonic reaction can be either slow or fast. Likewise, a slow reaction can be either endergonic or exergonic, and a fast reaction can also be either endergonic or exergonic. The slow-fast refer to kinetics, and the endergonic and exergonic refer to thermodynamics. Kinetics and thermodynamics are two independent parameters and not dependent on one another. Now I'd like to switch gears and talk about chemical reactions. Here's a cartoon that shows different types of chemical reactions. The first is combining two different molecules together, or two different types of atoms together to make one new molecule or one new type of thing. This type of reaction is called a synthesis. It's also called a combination reaction. The exact opposite of a combination or synthesis reaction is called a decomposition. This is when I take one thing and I decompose it into two separate individual things. Synthesis and decomposition are opposite of one another, but the words synthesis and combination are synonymous. The last type of reaction is an exchange reaction. Here's an example of a double exchange reaction where I have two molecules that are switching components. They're basically swapping partners. The exchange reaction is also called a displacement reaction. So exchange and displacement are synonymous. These are only cartoons showing chemical reactions. Now apply these labels to actual chemical equations. Pause the video now and try this activity. Then try to answer the questions underneath. The first reaction here is an exchange reaction, and it is actually a double exchange reaction. The second reaction is a synthesis. The third reaction is another exchange reaction, but this one is called a single exchange reaction. And the last one is a decomposition. If you'd like to check your work to the answers underneath these diagrams, please check the key. Now I'd like to focus on redox reactions. Redox reactions are reactions where electrons are moving around from atom to atom. The acronym redox stands for reduction, oxidation. And in these types of problems, we are going to try to identify the reactants that are oxidized or reduced. In order to identify these things, it is useful to remember the acronym OIL-RIG. OIL stands for oxidation is loss, and RIG stands for reduction is gain. And in both cases, we're talking about electrons. So oxidation is loss of electrons, and reduction is gain of electrons. There are two sets of rules, or two strategies for identifying things that are reduced or oxidized. In the first case, you want to pay attention to charge, and you'll find that things that become more positive are oxidized because they lose electrons, and things that become more negative are reduced because they're gaining electrons. This set of rules is really useful for inorganic reactions, and these can be identified because they do not contain carbon and they do contain ionic compounds. Anytime you are asked to identify the things that are oxidized or reduced in an inorganic reaction, you should keep track of the charge. On the other hand, if you have organic reactions, which are carbon-containing reactions with only covalent bonds, then you're going to pay attention to the loss or gain of hydrogen and oxygen. Let's do some examples to see how this works. Notice that the reaction in front of you is an inorganic reaction. It does not contain any carbon. Therefore, it fits into the purple rule category. And when we are doing this, or when we're trying to identify whether iron or oxygen is oxidized or reduced, it's helpful to use the table underneath the reaction to keep track of these things. In general, what you'll do is you will identify the elements in the reactants and products, and you will identify their charges. Notice over here that we have an ionic compound. The charges or oxidation states on the elements in ionic compounds can be read directly off the periodic table, or they can be inferred from the formula. Anytime that oxygen, for example, is in an ionic compound, you should know that because it's in group 6A, oxygen will always have a -2 charge when it's part of an ionic compound. So oxygen here will have a -2 charge in this compound. On the other hand, iron is a transition metal. So you can't read the oxidation state of iron off the periodic table, but you can infer it from the formula. Just like if you were to name this compound, you would know that iron in this compound has an oxidation state of 3. You can use this information to know that iron as a metal will always have a positive charge, and in this case, in this particular ionic formula, it has a charge of +3. A new rule that you should learn is that anytime a reactant or a product is written in its elemental pure form, it will have a charge of 0. This is related to our activity on matter. If you identify something that is pure substance and it's an element, then it will have a charge of 0 when you're keeping track of charges for oxidation and reduction reactions. Now let's fill in the table. For iron in the reactants, its charge is 0 because it is pure iron. The charge in the products, as we mentioned earlier, is +3. And so notice that iron is becoming more positive. Therefore, it fits into this category over here, or this left-hand box. The iron is becoming more positive. Therefore, you can answer this question. Did it gain or lose electrons? Well, if it became more positive, it has lost electrons, and therefore it was oxidized. Now let's keep track of oxygen. Oxygen in this reaction is in its elemental pure form, and therefore it has an oxidation state or charge of 0. In the product, oxygen is part of an ionic compound, and anytime oxygen is part of an ionic compound, it will have a -2 charge. You can also see this from the formula. If iron has a 3+ charge, oxygen has a 2- charge. During this reaction, oxygen is going from a charge of 0 to a charge of -2. Therefore, it's becoming more negative, and it's gaining electrons. This means that the oxygen has been reduced in this reaction. Anytime you have an inorganic reaction, you are going to pay attention to ionic charge to determine redox. You determine the charge of ions using the periodic table or inferring the charge of transition metals from the formula, just as you learned when naming ionic compounds. If you're doing an organic reaction, however, you need to use the second set of rules, and you will only pay attention to the gain or loss of hydrogen. For organic reactions, you use bonds to hydrogen and oxygen to determine their redox. Here's an example. On your activity, I've shown you the full chemical structure for nicotinamide adenine dinucleotide. This is a skeletal structure, and all of the little corners here are carbons, just like you would expect from any skeletal structure. So notice that this is a carbon-containing molecule, and this is also a carbon-containing molecule called ethanol. Because carbon is involved here, these are organic molecules, and this is an organic reaction. This reaction is showing that this molecule, which I abbreviate as NAD+, is reacting with the ethanol to give nicotinamide adenine dinucleotide with an extra hydrogen, so the hydrogen has gone here, and this molecule left over, which is acetaldehyde. The hydrogen that was on the alcohol of ethanol is now attached to nicotinamide adenine dinucleotide, and I represent this as NADH. The NAD is the representation for this large molecule, and the H represents the additional hydrogen that's been added. Notice that the ethanol originally had 6 hydrogens, and in the product, it only has 4 hydrogens. It has lost 2 hydrogens. One of them was picked up by NADH, and the other is lost as a proton. It's also useful to keep track of the bonds between carbon and oxygen. In the reactants, there's 1 bond between carbon and oxygen, and in the product, there's a double bond between carbon and oxygen. I'd like to point out before we go any further that this is a really important biological reaction. You will be talking about this in your biology class, but it probably won't be represented by the full chemical structure. Most of the time, biologists represent things by just an abbreviation like this one. They might write this same equation as NAD plus the structural formula for ethanol goes to NADH, so that H represents the hydrogen that's been gained, and the structural formula for acetaldehyde, plus a proton. The LAD here is an enzyme that you'll learn about later this semester. Enzymes are simply catalysts that make the reaction happen faster. For now, we can just ignore them, and anytime you see something over the arrow, unless told otherwise, assume it's an enzyme. Now, we said that for organic reactions, we were going to use bonds to hydrogen and oxygen to determine redox. So let's determine which of these reactants has been oxidized and which one has been reduced. Remember that oxidation is loss of electrons, and this can be seen by gain of bonds to oxygen or loss of hydrogens. Reduction is gain of electrons, and this can be seen by gain of hydrogen atoms or loss of bonds to oxygen. Notice in this molecule, I've gained a hydrogen, and in this molecule, I've lost 2 hydrogen atoms, and I've also gained bonds to carbon. Let's fill in the table, and I'm going to use the abbreviation here. The NADH has not gained or lost any bonds to oxygen, so there's been no change here. However, it has gained bonds to hydrogen, so this puts it into the category of reduction, and it's been reduced. Ethanol, we said, gained a bond between the carbon and the oxygen, and if you can't see it in this structure, look at the full structure to see what I mean. But it has gained bonds between carbon and oxygen, and it also lost 2 hydrogens. Therefore, it fits into the category for oxidized. Remember, for organic reactions, you're going to use the bonds to oxygen and hydrogen to determine redox. And for inorganic reactions, you use charge. Make sure you're using the correct rules. Sometimes you'll see a reaction that involves both an ionic compound and organic molecules, and you're going to use both rules in that case. There should be plenty of practice for you in the textbook and in the check for understanding. Make sure you check your key to make sure you're correct after you've practiced those problems. Thanks for watching this video on reaction energy diagrams and chemical reactions. If you have any questions, please post them in the comments, and if you like this video, don't forget to vote.